Good morning, guys. Oops, sorry, let me turn that off.
On what my Ukrainian colleague panelist said. I was surprised at saying
There we go. Okay, good morning. Welcome back to College Algebra, MAC1105. Today is one of those, well, today, it's one of those days where we introduce a new family of functions. So we're kind of into this part of the course now. We studied linear functions, and next we're going to start studying quadratic functions. From there, we'll study higher order polynomials and other bigger, more exciting families of functions. But today's one of those step days where we introduce a new one. So today we're going to begin talking about quadratics. I wanted to point something out in my open math that I did not notice. And hopefully it did not freak anybody out, but in the event that it did, I wanted to put you at ease. You may have noticed that, so what came due today? What came due today was homework 5 and quiz 5. You may have noticed that up until very early this morning, quiz 6 was also set to be due today, even though homework 6 was set to be due on Thursday. That was an accident. Quiz 6 was meant to be due on this Thursday, the 27th, not today. I must have just miskeyed the date when I put that in. So apologies if you felt that you had to panic and rush through quiz 6. That is not the case. If anybody had any sort of stress or issues around this, just let me know, and I can work with you on that. We can, like, if you used up your attempts or something like that, we can fix that. But yeah, obviously we hadn't lectured on quadratics at all. Homework 6 was not due, so quiz 6 was not intended to be due. It was just homework 5 and quiz 5 that were due today. So today we're going to begin talking about quadratics. Let me fire up the document camera. We can get moving on that. Oh, the other thing I'd like to talk about towards the start here is that your first test is coming up. Emberlyn, did you want to ask something or say something? An accidental unmute. I'm going to go ahead. Okay, so your first exam is coming up. It is on the syllabus scheduled to be this, is it this week, next week, this week? Certainly not going to be this week, right? Between the first week being a half week, we only met on Thursday. Class was not a thing on Tuesday of that week, and me getting sick around here kind of slowing us down. We are actually right here in the material. So this week, on Thursday, we're going to do our second activity. Next week, we will do the project and most likely the exam. So the most likely date for your first test, just so everybody's on the same page, is the 3rd, which is a week from Thursday, 10 days from today. Oh, here we go. So I'll get that stuff in writing just to make sure it's all nice and clear. First, of course, this is MAC 1105, section 015, which is college algebra. And the date today is the 25th of January, 2022. Today, we are going to talk about quadratic functions. We're going to talk about quadratic functions for several days. So we're going to introduce quadratics. And we're going to look at the graphs, forms of equations, let's say forms of expressions, yeah, and we'll talk about the quadratic formula a little bit. In the future, we are going to talk about complex numbers and how they connect to quadratics, because that's actually the very natural place to introduce them. Yes, Brent, the lectures are all recorded. They all go up on YouTube. A little announcement. So quiz 6 was not due today. There's a typo in my open math. So if that is something that caused you trouble, like you went in there, you were like, oh shit, quiz 6 is due today. I don't know this stuff, but you tried to take it anyway and you burned up attempts, send me a Canvas message or come by an office hour and we'll fix that. I'll restore those attempts. You are not meant to have to do that today. It will be due on Thursday. The other thing here that I want to talk about is exam 1. And that's the 3rd, I believe, right? Just triple check. Yeah. You know, barring anything crazy happening, right? If something crazy happens, then we may have to move it, but I don't expect anything crazy to happen. So yeah, you can plan for exam 1 to be next Thursday. All right, and the proctoring system there is the one that we described on the first day. So you will be taking your tests in My Open Math. They'll be proctored using HonorLock and your phone. So you'll have to have HonorLock on your computer, and you will join a Zoom meeting from your smartphone. Zoom is so I can see your desk, your hands, your paper, all of that stuff that, you know, I would normally be able to see if we were proctoring a test in the classroom. I want to be able to see that stuff. It's important. And then HonorLock will record your screen, your web activity, and all of that. Anything else under announcements here? No, I think that's about it. Any questions for me regarding this bookkeeping stuff, guys?
Real quick, is there like partial credit on the exam? Like if you get a question partially right, do you get credit for it?
Yes, so I'll be collecting work, written work from the test, and I'll review that written work for partial credit. So yeah, it's not binary. The test system is a new system. So this is my first semester teaching this class out of MOM. In the past, I wrote my own exams in Canvas. Right now, this section is a part of a pilot that was put together by one of our other professors here. So I'm going to have to talk to him and see how he's been structuring things, but I am a firm believer in partial credit. So yeah, there will be partial credit. I'm not 100% sure how he's structured the tests for this class, but if I have to change things to make that happen, I will. So yes, there will be partial credit. Any other questions about these sort of announcement stuff? I guess I should add, this is going to be during class, right? I know some online classes, you can like go to the testing center and take the test whenever you want. Not this one. Hybrid classes, that's the difference, right? Between a fully online class and a hybrid class. Hybrid synchronous classes, tests happen during class time, during normal class. Okay, so let's get to it. We're going to use Wabbit today. I'm going to be graphing some things in the graphing calculator. You do not need a graphing calculator to do any of the stuff that we're going to do today, but it is a useful way to check your work. I'm not sure on the number of questions, Kylie. So again, when I would write these tests, I would write them to be 14 questions long with like 4 true false, 4 multiple choice, and 6 or 7 free response. But again, this is a pilot class that's been structured by one of the other faculty, so I have to see what he's done. Okay, so quadratics. And there goes. We all have some familiarity with quadratic functions, I'm sure, from middle school, high school, wherever. The natural place to begin when we have a shared background like that is the definition. So a function f is called quadratic if it can be written in the form f of x equals, and we usually use a, b, and c for the coefficients. So if it can be written in the form f of x equals ax squared plus bx plus c. And this part, the bx plus c, is like a linear function, right? If you cover up the ax squared part, just this part would be a line whose slope is b and whose y-intercept is c. So you can think of this as a way of extending linear functions. Linear functions have constants and x to the 1 terms. Quadratic functions have those, but also x to the 2 terms. And our next section after we finish the unit on quadratics will extend these even further to have x cubed, x to the 4, x to the 5. But for now, right, a quadratic function, a function is called quadratic if it can be written in this form. And this form is generally called the standard form or expanded form. The numbers a, b, and c, the constants a, b, and c, are called coefficients. And they completely determine the quadratic. So if you tell me what a, b, and c are, then you've told me what the quadratic function is. There's only one quadratic with each set of coefficients. A is called the lead coefficient. And I'm going to abbreviate the word coefficient with coef. B is sometimes called the linear coefficient, although that's not always used. People don't always have a special name for B, but A is always called the lead coefficient. And C is always called the constant term. Okay. This form, the standard or expanded form, is not the easiest form to see the graph. So before we get to talking about graphs, I am going to show you a different form of writing these called the vertex form. We'll get to that. But before I do that, I just want to get one little bit of practice identifying the numbers a, b, and c. So identify the coefficients a, b, and c for, and I'll give us two functions to play with here. So how about f of x equals 6x squared plus 2x minus 3. And for b here, let's do g of x equals 4 minus 8x squared. So both of these are quadratics, I claim. And the question is, can we just say what a, b, and c are? And I think this is the easier one to begin with. So let's begin with this one. If we look at the function f here, this is of the form something times x squared plus something times x plus something else. What are those things? What is the lead coefficient a?
-6.
Yeah, very good, right? A is the number that's multiplying x squared. So this is -6x squared. So a is -6. What is b? Something in chat. Yeah.
Yeah.
Thank you, Catherine. Let me see. Yeah. B is 2. Okay, and C, what is the constant term here?
-3.
Excellent, -3. So be careful, right? In the definition here, these things are all kind of treated as though they're positive. So if you have a minus or a minus here, that means that the coefficient is negative. Some of the other forms of a quadratic have negatives built in. So you do want to be a little bit careful there. Okay, this one's a little trickier. Can anybody help me with the lead coefficient A, the quadratic?
-8.
Yeah, very good. So A is always the number that's multiplying x squared, and that's a -8x squared. So A is -8. What about B and C?
Would B be 0 because it doesn't exist?
Very good. Yeah, we don't see an x term anywhere here, which means B is 0. And I was thinking we'd have to come back to that one. Okay, what is 4? Damn it. What is C? Thank you, Haley. C is 4. What is 4? Okay, a quick little note. This guy could be written as g of x equals, that's what we're saying here. This could be written as g of x equals -8x squared plus 0x plus 4. That's exactly what we're saying when we say a, b, and c are these numbers, that we could also have written this function in this way. Any questions or curiosities about finding the coefficients a, b, and c? Okay, let's take a look at a graph. I'll never forget my first day of college algebra. I was 19 years old, 20 years old, 21 years old, 19, 20, I think, 20 years old. Came back to college after dropping out of high school, took 1033, and then the next semester took 1105. And the very first day, my professor in college algebra came in and told us to graph this function. And I remember being like, oh shit, I'm in trouble. But it's the only reasonable quadratic to start with. This, for everybody, should be the first quadratic graph they look at. And we're going to do it by plotting points. In the future, we'll have a way to graph these that's much faster. But for now, we're going to do this by plotting points. So if I want to do that, I can make a table. Okay, and maybe instead of making this table by hand, let me remind you, we can do this with the calculator. I'll show you how to do that. So first I'm going to turn on my calculator. If you have your calculator handy or nearby, please grab it. I'll give it a second. Grab that thing, turn it on. Maybe while we're pausing, I'd also like to remind, if you can turn on your camera, I would really appreciate that. Being able to see your faces and kind of see how you're following things helps me pace the lecture a lot, helps me tell if I'm doing a good job. So if you could, if you're in a situation where you can, please go ahead and turn on your camera. That would mean a lot to me. Thank you. All right. So while we are grabbing our calculators and turning on our cameras, making sure there isn't anything crazy in the background, I'm going to hit the y equals button in the top left corner here, which is how we enter a function, not just for graphing, but for any purposes. And then right there, y1, I'm going to type this button right here, which is the variable button. It's how you type in x, hit x. And then there's two ways to type x squared. There's a button here that has a little x squared thing. If I hit this, it will square whatever variable the cursor is on. So that's one way. The other way, I'm going to come back here and clear this all out. The other way is to come back here and type x. And then there's a little button here. It's called a caret. It looks like an arrow pointing up. It's just above the division symbol on the far right. If you type that, that will put you into an exponent. If you're on the TI-83, it'll literally type a caret. And what you'd want to do is type parentheses 2, close parentheses on the TI-83. On the TI-84, it visually moves you up into the exponent, so you don't need the parentheses. But on the TI-83, you definitely want to type the parentheses. So either one is fine. On the 84, I'm going to type it like this. And then I'm going to hit second and graph. So not just graph, I'm going to hit second and graph to bring up a table, because that's what I want, right? I want help filling out my table. I'm going to scroll back a little bit, because I want some negative values. Maybe I'll do -3, -2, -1, 0, 1, 2, and 3, just like we did for the absolute value function. So a nice place to get started. And then the things that are in the y column, those are my f of x's, right? The graph we always label as y equals f of x. So across from -3, I've got 9. Across from -2, I've got 4. Across from -1 is 1. Across from 0 is 0. And then those same things, just in reverse order. 1, 4, and 9 is what we'll find as we scroll down. Right? So generating that table is nice. Now we are going to plot these points. We're going to plot them by hand, and then we will check our graph against the graph generated by the calculator. What I see is that my x's are running from -3 to 3, but my y's, they're all positive. I don't have any negative y's. So I'm not going to make my y-axis poke down very much. I'm just going to do it like this. All right, and I'm going to choose slightly different scales. For my x-axis, I'm going to do like 1, 2, and 3. And we'll do the same scale on the negative side, -1, -2, and -3. But on my y-axis, I don't have like a bunch of space. If I spaced things out the same way, 9 would be like up here. So I'm going to chop it a little more like this. We'll do like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 8, 7, 8, 7, 6, 5, 4, 3, 2, 1. All right, I'm just going to label explicitly the ones that show up as outputs. I'm going to label my axes. The horizontal axis is the x-axis, the vertical axis is the y-axis, and I'm graphing the function y equals f of x. So it's nice discipline to go ahead and write y equals f of x on the y-axis. My points are -3, 9, this guy way up here. -2, 4, this guy right about here. -1, 1, 0, 0, +1, 1, +2, 4, and +3, 9. And the shape we get is a nice smooth curve found by connecting these points. So there are some similarities between this graph and the absolute value graph. He's kind of got this like downward pointiness to him, but he's nice and smooth. He's not like pointy at the bottom, just rounded. Right, that's the graph. This graph shape is called a parabola. Domain. You can see from the graph. Right, if you were to squish this whole graph down onto the x-axis, everything gets hit. These arrows indicate that this goes on and on like this forever. So it goes out forever and up forever. So there is a part that squishes down over here. It's just way up out on the left. So my domain is -∞ to infinity. And you'll see that's actually the same for all polynomials, all quadratics. The range is a little more interesting here. Can anybody help me with the range of this function?
Just 0, infinity.
Yeah, good. 0 to infinity. And of course, the infinity always gets a parentheses. What about the 0 here? Is there a point on the graph whose y value is 0?
It's a bracket.
Yeah, very good. Very good. It's a bracket because there is indeed a point on the graph whose y value is 0. This one right here. Okay. I'm not going to go through increasing, decreasing mins and maxes. There is a min right here. Right, the min at x equals 0, the min value is 0. We're decreasing from negative infinity to 0. We're increasing from 0 to infinity. But the point today is to learn about quadratics. So I want to talk about a few special features here. This point right here, it's called the vertex. I'm going to call it a turning point. Called the vertex. The whole graph, the graph shape, is called a parabola, which is an old Greek word. What it means is that if you were to draw a line down here and take the vertical distance from here to the point, some point in here called the focus, then that distance, the sum of those distances is always constant. That's the way the Greeks defined what a parabola is. They didn't know about quadratic functions, but they knew this shape from a purely geometric definition having to do with distances. Some neat facts about these. If I shine a light in from above, like this pen is a light, then the beam from that light will come down here, bounce off this, and hit this point. If I were to shine that light over here, say like this, straight down, then the beam from that light would come down here, bounce off this, and hit that same point. If I were to shine the light right in here, then the beam from that light would come down here, hit this point, and reflect right back up to here. This point is called the focus. And there's a reason, if you go out and look at your satellite dishes, or you look at radio receiver dishes, anything like that, they're all parabolic because they all have this really beautiful feature that if something comes straight in and bounces off of it, no matter where it comes in, it will always bounce to the same point. So what parabolas do, they focus things that come down on them onto a point inside of them called the focus. And on your satellite dish, that's exactly where the little receiver thing will be. So the little arm that pokes onto the dish and has a little sensor on it, that is sitting right at the focus of the parabola. So these things have meaning well beyond being the graphs of quadratic functions, and those other geometric meanings were understood long before we knew these were graphs of quadratics. That's the origin. The final thing I'll say about this while we're talking about fun facts about parabolas, they are one of a family of things called conic sections. If you take a cone and you slice it with a plane, as you see here, you will get one of a few possible shapes. If you slice perfectly flat, you'll get a circle. If you slice just slightly off kilter, you'll get a stretched out circle called an ellipse. If you slice like this, off kilter more, so the bottom of the plane does not come around the base circle here, you'll get a parabola. And if you slice straight up and down, you'll get something called a hyperbola. So these are the things that we're studying, parabolas, and that's how the Greeks originally thought of them. Before they had their distance definition, they thought of them as conic sections, slices of cones. But that's, for us, this is the graph of a quadratic function, and that's how I want you to think about it for now. Okay, so this is the graph of the function f of x equals x squared. It's made up of all the points whose x coordinate is any number and whose y coordinate is what you get when you square that number or multiply that number by itself. wouldn't it be nice if looking at the formula, you could tell what the vertex was? Moreover, if you know the vertex and one other point, any other point on the graph, you can tell me exactly what that parabola is, right? If I tell you the vertex is here and it also goes through this point, there's only one parabola that does that. So from the perspective of graphing, the most useful form to have the function written in is not the standard or expanded form, it's the special form that helps you read off the vertex. Okay, and this one is actually one of the few parabolas where those two forms are the same thing. So what I'm going to do is show you the vertex form, and then we're going to see how this fits into that, and then we'll use that vertex form to graph some more stuff. Yeah, that's it. We'll just leave it. So. Okay. I should say, we use special notation for the vertex. So the point right here, we'll just do it here. So if you can write your quadratic in the form f of x equals a, where a is still that same lead coefficient as in the standard or expanded form, times x minus h is a constant, all squared, like this, plus k. This is called the vertex form. Every quadratic can be written in this form as well. And some books, like the book that we teach pre-calculus out of here at Santa Fe, actually call this the standard form, which is very confusing. But most people call this the vertex form. And the vertex of the parabola is the point h comma k. And the number a is the lead coefficient, which is the same number as in the standard form. Okay. So if you know the lead coefficient and you know the vertex, then you can write down the vertex form of the parabola. If you know the vertex form of the parabola, you can sketch a really nice graph. The magic to go back and forth from one form to the other, the key to going from standard into vertex forms. Well, what do you need? If you're in standard form, then you already know A. A is the lead coefficient, same as in standard form. What you need are H and K. H will always be negative B over 2A, where A and B are the coefficients from the standard form. And K is the y coordinate of the vertex. So that's a point on the graph, which means to get that y value, you plug in that x value. So K is f of h, which is f of negative b over 2a. Because h is negative b over 2a. Mhm. So this is the form that is most useful for graphing. And this is how you go back and forth, or how you go from the standard form to the vertex form. All right, now the example we just did is kind of boring, but I'm going to go back to it really quickly and just show you that h and k are where they should be, and that this thing is already in that form. Yeah, maybe I should hold here for a second. Give you a minute to write. All right, make sure you get this nice and clear in your notes. This is important stuff. You'll need this a lot. Anybody need more
I have
time?
a question.
Oh, yeah, Samantha, go ahead.
So when you're doing the going into vertex form to get K, do you plug it back in F times the vertex form, getting the vertex for X?
I think what you're thinking is correct, but I want to clarify the language. So first you find h using this formula, and then to get k, you plug h in for x. And this notation, this isn't f times h, this is f of h. So this is the output you get when you plug h into the function f. So
But you plug it into vertex form.
you plug it into whatever form you have. So usually
Okay,
if you're
so
trying to go from standard to vertex, what you'll have is the standard form. So you'll use this formula to get h, and then to get k, you will plug that number in for x into whatever form you have.
all right, cool. Because I mean, I'm used to putting it back into like the quadratic formula, so I wasn't sure if there was another way.
The quadratic formula has utility, but it will not help us find the vertex. So the quadratic formula will help us find x-intercepts, which is nice. And we are going to talk about, there's a cool connection between the x-intercepts and the vertex. But for now, yeah, just think of h as this number that comes from the formula, and k is what you get by plugging that number in for x. So before we move on, let me come up here and show you how this thing can be written in vertex form. There isn't actually any work to do here. F of x equals x squared, I claim, is already in vertex form. I'll do this in blue. In vertex form. So A here, what is A? Remember, the lead coefficient is the same no matter what form you're in. So if you look at this right now, which is in standard form, you can see what A, B, and C are. Yeah, A is 1. Really quick, what are B and C? Good, B and C are both 0. All right, so this is 1x squared plus 0x plus 0. So A in vertex form is also going to be 1. Remember, because the standard form and vertex form, that lead coefficient A is always the same. H and K are the coordinates of the vertex. So what is H here? Yeah, good. They're both 0, right? The vertex here, this point is at the origin. It's 0, 0. So H is 0. That's the X value there, and K is 0. So if I plug those things into this formula, f of x in vertex form should be 1 times x minus 0 squared plus 0. X minus 0 is just x. That squared is x squared. 1 times x squared is x squared, and x squared plus 0 is x squared. So this really is the same thing, right? This guy is already in vertex form. We're just not writing the zeros. Okay. So let's get a little bit of practice. And let me pick something that will be nice here. Okay, so let's take the quadratic 3x squared plus 6x plus 1 into vertex form. And then sketch the graph. So this is in the standard or expanded form. And we said that the key to going back and forth from the standard to expanded form is to find the numbers a, h, and k. To get started there, I need to say what a, b, and c are. So what is a here?
Three.
3. Good. Yeah, the lead coefficient is 3. What is b? What is the linear term? 6. Thank you. It's in chat. And the constant term, c? That's 1. Excellent. Okay. So to put this into vertex form, I need h and k. We already know a. This will be the same in vertex form. We know that that vertex form is f of x equals, and you do need to remember this, a times parentheses x minus h all squared plus k. So we still need h and k. There's a formula for h. It's negative b over 2a. Right, and this is also something we just need to remember. B is 6, so that's negative 6 over 2 times a is 3. Ah, look at that. 2 times 3 is 6. So this is negative 6 over 6, or negative 1. So k is h is negative 1. How do I get k?
Plug in -1.
Yeah. K is always f of h. H is negative 1, so this is f of -1. So you got to go in this order, right? You got to find A, B, and C first. Then you use B and A to get H, and then you use H to get K. So the order that you do these things matters. Cannot start by finding K. If I want f of -1, I have to come back here to my formula for f of x and plug in -1 for x. So that's 3 times -1 squared plus 6 times -1 plus 1. And you need to be mindful of your order of operations. Let me show you how I would do this in a calculator. Not that you need the calculator for this, but if you're going to put things into the calculator, which I know we will inevitably do quite a bit of, quit there. This is 3 times parentheses -1, right? Remember, use this button for the negative, then close parentheses, caret squared, like that. If you're on the TI-83, you need to put the power in parentheses also. And then plus 6 times parentheses -1, and then plus 1. I get -2 out. Okay. So K is -2. Now I have A, H, and K. I have all the pieces that I need to plug into this formula and get my vertex form. So the vertex form of the function f is f of x equals A, which is 3 times x minus h, which is -1 squared, plus k, which is -2. All right, and be generous with your use of parentheses here. All of these parentheses are necessary. We can simplify in the next step, but for now, all of these are necessary. So if I want to simplify a little bit, that 3, he's not inside the parens or doing anything. But x minus -1, that's the same as x plus 1, subtracting a negative is the same as adding a positive. The square is still on the outside of the parentheses there. And then plus -2, that's the same as -2. So this is your vertex form. I would also accept this, right? Either one would be okay on a test. This is your simplified vertex form. This is just what you get when you plug in. If I wanted to graph this function, I can pull up my calculator. Actually, let's do it by hand first, and then we'll check with the calculator. I want to show you how to do this by hand. We need the vertex and one other point. Okay. So my vertex that's always the point h comma k. We found that already. You can read it off from here, or you can read it off from here. What is h?
-1.
Yeah, h is -1. So this is the point, -1 comma, what is k?
-2.
Excellent, thank you. Yeah, -2. Thank you also to Haley. Now to get one other point, what could I do? What could I do to get one other point on the graph of this function? Any other point, I don't care. how do we get points on the graph of a function if I have a formula for the function?
Do you plug in?
Yeah, we can plug in anything we want for x. All right, I can plug whatever you want in for x here. It's like part of making a table, right? When you make a table, you plug in x's, you get out y's, and those are points. So if I want to get any other point on the graph of this function, I can just plug in an x value. The only x value that it wouldn't be smart to plug in is -1, because I already know the point that's associated with -1. But I'll get the y-intercept. How about that? The y-intercept on the graph of any function, linear, quadratic, other functions, the y-intercept always comes from plugging in x equals 0. So let's grab that one. F of 0, you could do it from either form. Let's do it from here. That's 3 times 0 plus 1 squared minus 2, which is 3 times, follow your order of operations. First, work inside the parentheses. 0 plus 1 is 1. So that's 3 times 1 squared minus 2. 1 squared is 1. 3 times 1 is 1. So this is 3 minus 2, which is 1. So that y-intercept, that other point, is 0, 1. So I put the thing in vertex form. I know the vertex. I have another point on the graph besides the vertex. That's everything I need to sketch a beautiful graph of this function. Okay. The vertex is at -1, -2. So I'm going to need some negative y values. Y-intercept is at 0, 1. So let's do it like this. I'll call this -1, -1, -2, +1. So let me move this up. So my vertex is at the ordered pair -1, -2. That means I go left on the x-axis and down 2. And I know this is going to be a parabola. The y-intercept is right here at 0, 1. So this parabola is going to look like this. Like this. Okay, this is the graph y equals f of x. This is the x-axis. Not too shabby and not too hard. Maybe I'll write that vertex form over here again, just so we have it. That's 3 times x plus 1 squared minus 2. Okay. There are some other features here that I want to talk about, other features on the graph. You notice the graph of this parabola and the graph of all parabolas, they're symmetric about a certain line. That line is called the axis of symmetry. And it's always the line x equals h, where h is the x coordinate of the vertex. So here, that's the line x equals -1. The other thing that I want to mention at this point is that if I were to change this just a little bit, and make the lead coefficient negative, what that does is it flips the parabola over its vertex. So instead of opening up, it would now open down. So this guy right here still has vertex h comma k, where h is -1 and k is -2. But a here is -3. So the parabola opens down. In other words, if your lead coefficient is positive, your parabola opens up. If your lead coefficient is negative, your parabola opens down. There's a good question in chat. Is there an easy way to find the number a from the graph? Not necessarily. Not necessarily. There is, I'll tell you. There's something, if you ask the tutors in the library, here's what they'll tell you. If you go from the vertex 1 point over, right, you take a horizontal step of 1 point, then A will be the vertical step to the next point. This only makes sense if your vertex has integer coordinates. You can get in a lot of trouble if you apply this rule in general, but that's what the tutors will tell you. I would say the best way to find A is by plugging in a point that you know is on the graph and solving for it. But it's also the vertical step from the vertex to a point 1 x coordinate over. So the graph I'm drawing here is the same graph, but instead of opening up, it's going to open down. And the only difference between the formulas is that here A is negative, whereas there A was positive. And if you like, you can apply that rule that I just described, or if you take a step 1 over, then the vertical step will be in A units. So before we took a step from -1, x equals -1 at the vertex, over to x equals 0. And we saw that the y-intercept there was, what was it, +1, right? Which was 3 units up. Here, since A is -3, when I take a step 1 over, I will take a step 3 units down. So to go from -2 down 3 units, my new y-intercept here is the point 0, -5. And my vertex, -1, -2 still. And the axis of symmetry hasn't changed. The axis of symmetry here still the line x equals -1. So the closest thing to a direct connection between the number A and the graph is it's the vertical step between the vertex and a point 1 unit to the right of the vertex. That's a cheat code. That's not something I'm supposed to tell you, but the tutors are going to tell you anyway, so I might as well. Okay. So in summary here, If your lead coefficient is positive, your parabola will open up. And if your lead coefficient is negative, your parabola will open down. Once you know the vertex and you know any other point on the graph, you've got everything you need, including the information about whether it opens up or down. But sometimes, if you're just trying to draw a really quick graph, you don't care so much about finding that other point as you do just saying, okay, here's the vertex and the thing opens up. Questions about what we've described here? Okay, let me pull up Wabbit. We can check our graphs. So if I wanted to graph these things in the calculator, turn it on, I hit y equals, I'm going to type my function in. You can type it in any form you want. Just for shits and giggles, let's type this guy in the standard form, the form that he was first given. We can see how good a job we did converting to vertex form and graphing. Here we can compare. So I'm going to type 3x raised to the 2, and then I'm going to hit over so I get out of the exponent, plus 6x plus 1. And I'm going to adjust my Windows settings so that I'm looking at the relevant part of the graph. So right now I'm at the standard scale, standard settings. I'm not looking at any x values here, which are to the left of like -5. I'm not looking at any x values here, which are bigger than like 2. Y values are running from -2 up. So let me just say like -3 to give us a little bit of space, and +5, something like that. There we go. Very nice, right? It's just how we thought it did. If we wanted to approximate some points, we can use the trace function. That'll walk us around on the graph and give us an idea for where things are. Like here, we can see the y-intercept when x is -0.1, which is very close to 0. Y is like 0.9, which is very close to 1. Doesn't give us the exact value. The vertex, you can see down here. Again, this thing is not going to, trace function is not going to give us exact values. But when x is very close to -1, y is very close to -2. And the parabola looks how we'd expect. What I would like to start talking about now is how to find the x-intercepts. So these guys, the points where the graph crosses the x-axis, those can be a little bit tricky to find. To be clear, y-intercepts are always easy to find. The y-intercept is never hard. You just plug in 0 for x. If you plug in 0 for x, these go away, you get 1, right? Finding the y-intercept is always easy. Just plug in 0 for x, and that's true for any function. X-intercepts are a whole other ballgame. There are a few strategies for finding x-intercepts. Generally, what we're trying to do here is we want to solve the equation f of x equals 0. You're trying to find where the y values are 0. That's what an x-intercept is. The main strategies, so you've got several options. One, if in standard form, you can try to factor. I'll show you how to factor and how that gives you the x-intercepts. If in vertex form, you can set f of x equals 0 and solve by taking square roots. And if all else fails, you can use the quadratic formula, which I will show you. And I will embarrass myself for you to give you a way to remember it, that you'll always remember. So factoring. Some factoring problems are easy, others are hard. I want to find the x-intercepts for the function f of x equals x squared minus x minus 6. The most general method is called the AC method. A slightly abbreviated version of that is where you look at this number. So if a is 1, if you just have x squared instead of some number like 2 or 5 or 7 x squared, then what you can do is look for two numbers that multiply to this and add up to this. So can I think of two numbers so that when I multiply them, you get -6, and when you add them, you get -1? Anybody help me with those?
-3 and +2.
Yeah. This means that I can write x squared minus x minus 6 as x minus 3 times x plus 2. And you can check by foiling. Hopefully we all remember how to foil. You take your firsts, that's x times x, which is x squared, your inners and your outers, so that would be x times 2 or plus 2x minus x times 3 or minus 3x, which is minus x, and then your lasts, minus 3 times positive 2 is -6. So f of x is equal to 0 means x minus 3 times x plus 2 is equal to 0. And there's a rule that says if you have two things multiplied equaling 0, then one of them must be 0. So the only way for this to happen is if x minus 3 equals 0 or x plus 2 equals 0. This last guy is the same as saying x equals 3, and this guy is the same as saying x equals -2. So those are your x-intercepts. There is a slightly more advanced version of this, where if this number is not 1, then instead of finding two numbers that multiply to just the last term, you have to multiply both of these. So for full factoring tricks, you'd use what's called the AC method. Now, this is something that I'm supposed to assume you've learned before. I wanted to review the simple version of it quickly. But in case you haven't seen it in a while, I had a good one here, yeah. Here is a video to refresh the AC method. I'm going to paste this in chat. If you need to remind yourself how to use the full AC method, please do that, right? Because factoring like this is something that you're going to need to be able to do. You're going to need to be able to do it quickly, including the more advanced versions where there's like a 2x squared here. I'll work some examples like that, but not right now. In vertex form, if you happen to be in vertex form, like that one we were looking at a second ago, it's what, 3 times x plus 1 squared minus 2. If you are in vertex form, you can find the x-intercepts by setting this equal to 0 and solving using square roots. What do I mean by that? So we're going to set f of x to 0 and solve for x. You can't do this in standard form because you've got x squareds and x's floating around. You have to factor if you're in standard form. But if you're in the vertex form where the variable only shows up in here and that whole thing is raised to the 2, then we can do this. You can solve kind of barehanded. No fancy tricks. So f of x is 3 times x plus 1 all squared minus 2. And I'm going to set that equal to 0. My aim is to get this x alone. So I'm going to start by adding 2 to both sides. That gives me 3 times x plus 1 all squared equals 2. Next, I can divide both sides by 3, and that gives me x plus 1 squared equals 2/3. Next, I will take square roots, and when you take square roots on both sides, on the left, you get x plus 1. On the right, you get plus and minus the square root of 2/3, like that. Whole thing under the square root. And finally, subtract 1. So I'll write that as -1 plus or minus the square root of 2/3. And this is a pretty nasty number. If you look at the graph that we generated in here, we still have it. Yeah, these x-intercepts are indeed nasty, nasty numbers, right? They're not nice. This is not a whole number at all. It's not a rational number. It's not even a nice fraction. It is a nasty, nasty number. So we get here the two answers. X equals -1 plus the square root of 2/3 and x equals -1 minus the square root of 2/3. And then the last thing here is the quadratic formula. On Thursday, we're going to talk more about all this stuff, and I will show you how the quadratic formula connects to the vertex. There is a neat relationship, but for now, because I want you to just have the things that you need, I'm going to share with you the quadratic formula, and I will debase myself. If you want to remember the quadratic formula forever and ever and ever, here's what you do. You phone up your crush or someone whose opinion of you matters a lot, someone you want to like you. And you sing to them X, I'll write it first. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. You see, you do that and you will embarrass yourself so deeply and intensely that it will sear its way into your brain forever and ever. It'll be one of those things that wakes you up in the middle of the night going, why the fuck did I do that? But you'll never forget the quadratic formula. The context here. If f of x is ax squared plus bx plus c, then f of x equals 0 if and only if x is one of these two numbers. Okay. That is the quadratic formula. So these are the x values of the x-intercepts. It works. Yeah, it really does. It's painful, but it works. So if you've struggled to remember this in the past, singing it like that, especially in front of somebody that you can be embarrassed to, is surprisingly effective. All right, let me take a quick glance at your homework, make sure I'm not leaving you high and dry on anything here. I don't believe we are. We've talked about how to find x-intercepts, how to find y-intercepts, how to find vertices. Yeah, how to find the axis of symmetry, how to factor. I think you're Gucci, guys. So work on this homework set. If you do get stuck on anything, I have an office hour today from 11 to 12, another one tomorrow from 1 to 2, and I'm happy to talk you through any of those things. On Thursday, we will talk more about quadratics. I will help you see the quadratic formula in some context. You'll notice this -b over 2a part of the quadratic formula. That is what it looks like. That's the x value of the vertex, and there's a cool thing there. But for now, I just want you to practice. I want you to practice graphing. I want you to practice going back and forth from standard form to quadratic form. Make sure you're comfortable doing things like foiling and factoring, the stuff that you're supposed to know coming into this class. Make sure that you not only know it, but you're comfortable doing it and doing it quickly and without errors. If you struggle with any of that, or if any of it's making you nervous, please come talk to me in office hours, send me a Canvas message, show me some of your work. That's the best thing you can do. But that's it from me for today. I'll see you guys on Thursday. A little note, Thursday, we're doing an in-class activity. All right, so remember, those cannot be made up if missed. Make sure you come here on Thursday. Do not miss. All right, take care.